Hello, in this video we will summarize the generalized integrals or the improper integrals. First, when we have a function f piecewise continuous on an interval ab, where f is defined for instance at b but not at a, we define the generalized integral of f between a and b as the limit when x tends to a of the integral from x to b of f of t dt. When this limit exists and is finite, we say that this integral is convergent to the value of this limit. In a similar way, we can define also the generalized integral when f is defined at a but not at b. b can be infinity in this case. When the integral is not convergent, it's of course divergent. We will talk about four topics. First, the Riemann functions and some cases where the integral can be calculated. Second, we'll talk about some general results. Third, about some convergence criteria for positive functions. And last, we'll talk about the absolute convergence. So, how can we find the value of the integral sometimes? In fact, sometimes when the primitive of a function can be determined, it's interesting to calculate the primitive, then the limit at the problematic point of this primitive. If the limit is finite, then the integral is convergent. We'll consider also one special case. It's the case of the Riemann functions. These functions can be written as 1 over x to the power alpha. The integral of this function between 1 and infinity is convergent only when alpha is greater than 1 strictly, and it's divergent in the other cases. On the other hand, the integral from 0 to 1 of this function is convergent only when alpha is less than 1 strictly and divergent in the other cases. Let's now give some general results. First, the sum of two convergent integrals on a, b is a convergent integral, and its limit is equal to the sum of the limits, while the sum of a divergent integral and a convergent one on a, b is divergent. Finally, the sum of two divergent integrals can be either convergent or divergent, so no conclusion can be made in this case. Now, when f is defined on an interval ab, while f is not defined at a, neither at b, then if there exists c in ab such that the integrals on ac and on ca are both convergent, then the generalized integral on ab is the sum of these two integrals. If we consider now an integral on ab of a function f such that f is not defined only at a, then if the limit of f at a is finite, the integral is convergent and the integral is called falsely improper. If we have now an integral of function f defined on a plus infinity, then if the limit of f at plus infinity is not 0, then the integral on a plus infinity is divergent. Finally, the integral of an even function on minus a, only when it's convergent, is equal to 2 times the integral on 0a. And the integral of an odd function on minus a, only when it's convergent, is equal to 0. Let us now check some criteria for the convergence of generalized integrals of only positive functions. First, the generalized integral on ab of two functions, say both not defined at b, but equivalent about b, are either both convergent or both divergent. As shown in the example, it's very common to use the equivalence criteria to compare with the Riemann functions. Another criteria is the comparison criteria. If f is less or equal than another function g on ab, then if the integral of g converges, the integral of f converges. But if the integral of f diverges, then the integral of g diverges. Finally, we can also use the negligibility criteria. It says that if we have two functions f and g, say both not defined at b, but f is negligible with respect to g about b, then if the integral of g on ab is convergent, the integral of f on AB will also be convergent. Now, what about the absolute convergence? A generalized integral of f is absolutely convergent if the generalized integral of the absolute value of f is convergent. Now, the absolute convergence is a strong condition. We can therefore prove that if an integral is absolutely convergent, then it's convergent. The converse is not true though. We have the equivalence between both the absolute convergence and the convergence only when f is of constant sign on the integration interval. Hope you got it all.